Good afternoon. All right, we do have a daily quiz today. Shouldn't take too long. Sorry, I'm trying to make sure I can sign in, but it's 1 o'clock, so let's go ahead and do that. Daily quiz. While I try to get my iPad working. So, daily quiz for today is, do the vectors 1, 0, 0 and 0, 1, 0 form a basis for R3? Do the vectors 1, 0, 0 and 0, 1, 0 form a basis for R3? All right, 3 responses so far. All right, we got all 6 responses. I'm going to just give you all an extra 10 seconds to look at it. Make sure you are sure on your answer before I lock. All right, locking answers in 5, 3, 2, 1. Locking answers now. And I don't know why some of you switched from the right answer to the wrong answer at the last minute. I didn't mean to make you second guess yourself, but it happened. So, just a weird thing to see, I apologize. So, I'm going to need some people to unmute themselves because I'm going to ask you 2 questions to form a basis. A basis for a vector space. I'm just going to shorthand VS here for vector space. We have to have a set of vectors, and those vectors have to satisfy 2 things. What is one of those 2 things?
They have to be independent?
Yeah, they have to be linearly independent. Absolutely. That's the first thing, and then what is the second thing?
They have to be in the span.
So yes and no, and it's just the way you said it. I think the intent is there. So the span of those vectors, so whatever they are, v1, v2, all the way to vn, that span has to be the same thing as my vector space. So they span the vector space. Anything in the vector space can be written as a linear combination of those vectors, right? This is not an official definition. This is just kind of a reminder of the 2 things that they have to satisfy. So I have to look at these things, these 2 vectors, and say, a 1, 0, 0, and 0, 1, 0. Are they linearly independent? What do y'all think? Yes or no? You answered the question, so you shouldn't have an opinion on this, right? Are these two
No.
vectors? What was that?
I guess it's no.
Yeah, they actually are.
Wow.
Here.
So real quick,
What was that, Josh? Sorry.
if I could go back and change my answer.
No, sadly. But they are linearly independent, right? If I try to write this as a linear combination that equals the zero vector, how we always test for linear independence or dependence, I combine that left-hand sign. What this tells me is that C, for that equation to be true, C1's got to be 0, C2's got to be 0. So we do get that they're linearly independent. These two vectors are linearly independent. However, what about that last one? Right? In this case, the vector space that we're working in is R3, which means it's any vector with 3 numbers in it, right? X, Y, and Z can represent any real numbers. These are the things that live in R3. So can I create any vector in R3 with just these two vectors?
No.
Yeah, answer is no. That's one nice little simple example. 0, 0, 1 is in R3, right? It is a vector with 3 entries. But I can never find any coefficients for those two vectors, so C1 and C2, such that when I add them together, I'm going to get 0, 0, 1, because in both of these cases, that bottom row is a 0. There's no way I can add zeros together to get something that is non-zero, which is a 1. So in here, it's that last one. Yes, these two vectors are linearly independent, but they don't span R3. They can't recreate any vector that is in R3. Okay, so the correct answer is no. These do not form a basis because they don't satisfy those two conditions. So questions, and same thing for a lot of y'all in the Calc 1 class as well. If you got no questions, give me a thumbs up so I have a cue to move on.
Wait, I have a question.
Yeah, go for it, Josh.
Great. So when I said, let me change my answer, and you said no, you were saying no to the vector space, right? Not the basis.
Sorry, I thought you were saying I want to change my answer to the daily quiz. That's why I inferred.
Yeah, because when I answered no, I thought you was talking about do they form a basis.
Yeah, I thought you were saying that the answer was yes when you answered him.
No.
Me too. That's what I thought.
I'm going to have to look at this recording because I have no recollection of ever saying that. So, yeah, this does not form a basis. Not form a basis. But I mean, I locked the answers before.
Oh, I thought you said.
Because you had me confused. I was like, so it's yes? I was like genuinely confused.
Okay, how? So, no, this is just to help me out. I apologize for having to flip it on y'all. You be the instructor and I'm the student right now. So, what did I say that confused y'all?
Okay, so when you ask a question, do they form a basis? I said no, and then you said yes. But I think you mean you're saying yes to the vector space probably. And
So the question, are you talking about the question in Poll Everywhere?
yeah, I pressed no, and then when I said no, you said answer was yes, and then I was like, can I change my answer?
Yeah.
Yeah.
Oh,
I think you were talking about if it
Yeah,
was
that's what you said.
linearly independent.
yeah.
I think that's what you
Yeah,
thought.
I think that's what the question was.
Okay, yeah, because to answer the overall question, we have to answer the two sub questions, right? Is it linearly independent? Does it span the set? So, okay. I think I'm slowly finally catching up with y'all. So the answer to the overall question for the daily quiz, is it form a basis for R3? The answer is no. They are linearly independent, but they don't span the space. So is everyone on the same page now since I confused us on accident?
Yeah.
Yeah, we're good.
Cool. All right. Usually it's the other way around. I'm supposed to be confusing y'all. So this is weird.
I ain't good. I ain't good.
That's
I
why I
ain't
like
good.
to stuff.
I get it wrong, so me ain't good.
All right. So any more questions? Otherwise, we're going to keep going on.
I don't have a question, but
Okay.
right now I'm at work, so I'm trying my best to stay in class.
Okay. Worst case, so we're not going to be doing any more poll everywhere questions. I just wanted to make sure you had a daily quiz so you can get more grades in there. We're going to be kind of sticking to the Zoom whiteboard, and I think I already said worst case, but worst case, if you have to miss like a small section of class, just try to keep an idea of the time, because I'm posting the recording of the class up soon after this, and you can go back to the video. Of course, I don't think we'd like that to happen, but it's a worst case scenario. But thank you for giving me that heads up.
I have a question.
Yeah, what's up, Nabari?
So for R3, to have a span, would it need to have 3 elements with 3 columns alone?
Yep. So for R3, we'll actually see that, and it's actually part of what we're talking about today, called dimension. That for, whoops. We'll just write out for a set of vectors, to form a basis for R3. Wow, for a set of vectors. Wow. Just for a set of vectors to form a basis for R3. This is a weird way to state it grammatically now that I'm reading it again. But there can only be 3 vectors. Because what happens is, as we just saw with this daily quiz, if there's only 2 vectors for R3, you're probably not going to be able to, well, you won't be able to span the entire set. There's going to be some vectors that you won't actually be able to recreate, just 2. And then if I had 4 vectors at all, I'm going to see that I'm going to fail linear independence. So there's this nice little trade-off, and this is why we care about studying basis, because they're this set that have the perfect amount of vectors with the right property. And when those two things come together, I have my building blocks for any space. So that's a great motivating question. Thank you for asking.
Wait. I have a question now.
What's up?
So you said there can only be 3 vectors, not 3
That
ends.
set. Huh?
Not 3 ends, as in the R3. It's 3 vectors.
3
The end-
vectors.
the
We're
end
working
can
in
be-
R3. This is our umbrella, and when we're picking out vectors to try to form a basis from R3, there has to be 3 of them. There can be no more than 3, no less than 3.
3
You still-
vectors, 3 entries in each vector.
3 vectors,
But you can only have 3 entries in each vector.
because we're in R3, yes.
Why can you only have 3 vectors though?
Just like I said, if you have more than 3 vectors, you're going to fail linear independence.
Yeah. Okay. Yeah.
Less
Yeah.
than
Yeah.
3 vectors, you're going to not be able to span. Yep. And that's what we've seen, right? For, I can't pull up the example, but the daily quiz. You only had 2 vectors. You weren't able to satisfy the span. If, I think you get it in the homework, there's one where you have 4 vectors in R3, I think. You quickly see that they're not linearly independent. You can write at least one as a linear combination of others. So let's do definition. This is that dimension. So let V be a vector space. So I'm using a capital V here. Again, capital V for vector space. If V has a basis, so if that vector space has a basis, consisting of n vectors, and we say that the vector space V has dimension n. Commonly, instead of having to say vector space V has dimension n, there's a nice little shortcut notation. We think of dimension as a function. So you're going to constantly see it written as dim for dimension of your vector space. You can write that V a little bit, is equal to n. So dimension is just saying, once you find a basis, how many of those vectors are in that basis, and that number is your dimension. All right, so we've already done some examples. I'm going to give you all just a couple more seconds to finish writing down that definition. Also gives me a second to sip my tea. So I can answer questions something like this, like what is the dimension of R3? Well, we know R3 has the basis 1, 0, 0, 0, 1, 0, and 0, 0, 1. Something we can show these 3 sets, this set of 3 vectors are linearly independent. They will also recreate anything in R3 as long as I combine them, create a linear combination of these 3 vectors. So I have a basis in for R3. How many vectors are there? Yeah, just 3. So the dimension of R3 is 3. Dimension of R3 is 3 because I have found a basis for R3 and I just counted up the number of vectors in that basis. And we also know, this is just kind of a reminder, this wasn't the only basis for R3. We also showed, I think last Friday, or last Tuesday, let's see, no, Tuesday, today's Tuesday, days are running together, sometime last week. That this set of vectors, 1, 0, 0, 1, 1, 0, and 1, 1, 1, whoops, 1, 1, 1, also are a basis for R3, but hey, conveniently look at how many vectors there are in there. There's 3. So in R3, we can already kind of see, write it in blue, a set, and this is what we were talking about after Nabari's question, right? In R3 for a set of vectors.
Professor, I have a question.
What's up?
Can you do an example where you give us vectors and you find the basis and then you find the dimension?
That's the plan.
Thank you. Sorry about the interruption.
No, you're good. R3, so there's be basis in there. Only be 3 vectors. I had to kind of jam it in there in the bottom right, that last word is vector. So in R3, for a set of vectors to be a basis, then we know that there can only be 3 vectors. Since we now know what the dimension is. Any less than 3, if it's less than 3, it won't satisfy linear independence. If it's more than 3, it won't satisfy the spanning. Or sorry, flipped. If it's less than 3, it won't satisfy the spanning property. If it's greater than 3, it won't satisfy the linear independence property. So then real quickly, let's answer a couple more questions. Not Rn. Let's do R2 first. What do you think the dimension of R2 is?
Two.
Yeah, it'll be 2. But if it's 2, that means you're going to have to find me a basis for this, right? And in that basis, there can only be 2 vectors. So I have to make sure that I'm able to state a basis first to verify that the dimension's 2, but you're right. So what would be a nice, easy basis for R2? What 2 vectors?
1, 0, 0, 1.
Yep, perfect. That is a basis for R2. These are linearly independent, and they'll be able to recreate anything in R2. So yeah, this has dimension 2. I'm not going to ask you to write me a basis for this one. What do you think the dimension of R4 is?
Four.
Yeah, it'll be 4. Nice, easy basis that I could create. 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 1, 0, and 0, 0, 0, 1. Though we also saw on Friday, that's not the only basis. It could also be 1, 0, 0, 0, 1, 1, 0, 0, 1, 1, 1, 0, 1, 1, 1, 1. We showed on Friday that that collection of vectors forms a basis for R4, but again, how many vectors are in there? There are 4. So then in general, we're not going to prove it, but I think we can establish a pattern just from those 3 observations. If I'm considering just a general Euclidean space Rn, what should the dimension of Rn be? Let's go Chevy. I'm gonna pick on you. What do you think it should be?
I'm finding the basis of it.
Oh, just the dimension. Technically, yes, but I'm asking you to extrapolate. So we said, dimension of R3 was 3. You've now also said the dimension of R2 is 2 and the dimension of R4 is 4. So in general, the dimension of R to the n will probably be what? Yeah. That is a fact. Dimension of any Euclidean space depends upon essentially how many entries you have in each vector. And that also tells us if I want to create a basis for R5, I'm going to need a minimum of, or I'm going to need exactly 5 vectors. Okay. So just a couple more definitions or notes about this definition dimension, and we'll start dealing with more examples. So the vector space, which is a space that only contains the 0 vector. And this is a vector space. It does satisfy all of our axioms. But this vector space is said to have dimension 0. That's just a common thing. It's a way that we can talk about zeros. And the only time your space should have a dimension 0 is if it only contains the 0 vector. Otherwise, it's going to have at least dimension 1. So that's the first thing. Second thing, your vector space V is finite dimensional. If a basis has a finite number of vectors. And second, on the flip side of that, it's infinitely dimensional, or is infinite dimensional. If a basis has infinitely many vectors. So there are both finite dimensional and infinitely dimensional vector spaces. Usually, whenever we're doing matrix theory, even when you get to a higher level, we like to stay in finite dimensional because things work nicely in finite dimensions. And once you get to infinite dimensional, things start breaking down and they get weird. You can start asking some very, very, very interesting questions, but it becomes harder and harder to answer because remember, your basis is your building blocks, right? We're saying a finite number of building blocks. That means I can count the number of building blocks that are there. So I have a handle on what I can use, and then I can also see from that what I can build. If there's infinitely many building blocks, it's really hard to figure out then what you can build, all the different types of things you can build. So just an example of some examples setting these up. One of the spaces that we have seen in our homeworks, a set of polynomials of degree n or less. And we've usually seen it with this capital P, bold case, P with an n to the power, P to the n. This is a vector space. Right, so any polynomial of degree n or less, that entire set forms a vector space. And just the note, if you're a little confused, all elements in Pn are of the form a to the n, x to the n, plus a to the n minus 1, x to the n minus 1, plus a2x squared, plus a1x, plus a naught. So just polynomials. Any polynomials that you can think of. And this does have a basis. I'm going to need a 1 to recreate any constants, I'm going to need an x. To recreate any x terms, I'm going to need an x squared, x cubed, and so on all the way up to the x to the nth power. So for any Pn, I'm always going to have these types of elements. These x's are going to form a basis, which means that the dimension of p to the n is going to be equal to what? And be careful. What is the dimension of p to the n going to be? I can see some people are finishing writing this down, but still at least give me a guess. What do you think is it going to be?
1.
Not 1, because if it was 1, that would say my basis has a single element in it, right? As we can see right here, that's not the case. How many elements do I have in that set, in that basis? But thank you for also speaking up and giving me a guess.
N number.
Close.
Infinite? Oh, n plus 1.
Plus 1, right? It's always the highest degree term that I can reach. X to the n minus 1, so that'd be 2, x to the n minus 2, 3. I'd keep counting down. I'd have n numbers of x's, n x's terms in there. And I also have to count for the constant term, and it is 1. But since this is not an infinite number, it's always going to be set. This is a finite dimensional vector space. This is a finite dimensional vector space. Okay. So I got to get a new.
Why is it n plus 1? Why not just n?
So let's work in less general then. Dimension of P3. Actually, let's keep it simpler, P2. So this means I'm looking at all quadratics or less. So a2x squared plus ax plus a naught. Right? A2, A1, A0 can be zeros, they can be 1, they can be whatever. This is what those polynomials in this set look like. Which means my basis will need what terms in it? What are the 3 building blocks for any quadratics?
1.
Yep, I need a 1, because I can multiply 1 by anything to get whatever a naught needs to be, my constant term. What else?
X.
Yeah, I'm also going to need an x to get whatever my linear part is, that a1 to the x, and then what's the last thing that I need?
A.
What was that, Josh? Sorry.
I guess A.
Wouldn't it be x squared?
Yeah, it'd be an x squared. So to create any general quadratic, we know that there can be an x squared term, an x term, and then a constant. And these are the 3 things that are going to build all of those parts for me. My x squared term, this will build my x term, I use to build my x term, this I use to build my constant. So that is a basis for the set P2. How many elements do I have in that basis? Yeah, I see you raising it up there. I have 3. So the dimension of P2 is 3. If I did the dimension of P1, this would just mean all linear terms. So a1x plus a naught. What would be the basis for this?
I mean, the base would be 1 and x.
Yeah, basis would be 1 and x, and you're answering the question I was going to ask next, which is what is the dimension of this, of P1, which would be 2. See, it's just, you have to make sure you're looking at all the terms. That's why it's always 1 greater than whatever your n is for the p to the n. Because you're going to have n terms with x in it, and then you also have to account for your constants, and that's kind of where that plus 1 is coming from. Okay, so polynomials. Polynomials are finite dimensional vector spaces. R4 is a finite dimensional vector space. Right? Because the dimension of R4 is what?
4.
Yeah, it's a finite number. However, we're not going to go into infinite dimensional vector spaces like I said, but there is an example of an infinite dimensional vector space that we've seen, and you actually study a lot, especially y'all in calculus, which is the set of continuous functions on a closed interval AB. Oops, let me rewrite that. Continuous and you'll usually see this written as C A B, that capital C representing continuous. This is just the, I'm going to underline it in blue here. This is the notation that we use to say, hey, this is the set we're talking about, so I don't have to write out continuous functions on a closed interval AB every time. But this is an infinite dimensional vector space. Any basis that you are able to come up with will have an infinite number of vectors in it. We're not going to touch on why, though you can just see that any polynomial, it will be in CAB, which means there's no height on how high the degree of those polynomials can go. So just from that fact in general, there's an infinite number of things, but that also doesn't include, you know, square root. Square root function can be potentially continuous on the closed interval AB. You can also have your logarithmic functions, exponential functions, your trig functions, things like that. There's just so many things in there, in that space, that we can't just nail it down to a set amount of things that allow us to, or a finite amount of things that allow us to build everything in this set. Okay, so I do want to get to example like Eliam requested, but questions so far, because we're kind of staying conceptual right now. All right, not hearing anything. So this is the example I wanted to do today. Given the vectors, I'm going to have this set 2, 3, 1, 1, 1, 1, and 3, 5, 1. The question that we're going to ask is, what is, I'm writing this improperly, setting it up properly. I'm just going to refer to that first vector as x1, the second vector is x2, and the third vector is x3. Question we want to ask is, what is the dimension of the span of these three vectors? Which is, what is the dimension of the span of these three vectors? So we got 11 minutes left. I'm going to lead us off, but then at one point I'm going to ask y'all to work on your own just for a moment. Okay. So if I'm trying to find the dimension of this span, that means I need to find a basis. Right? So I need to find a basis for this span. And then once I have a basis, the number of vectors in that basis is going to tell me the dimension of this span. Because this is a vector space. Okay. So, what is a logical starting point? What set of vectors could I go ahead and test to see if they form a basis? See, I don't want to pick on Liana because she said she's at work. She might not be there. Josh, I'm going to pick on you now. What's a good set of vectors to start with? Just to see if they form a basis.
I think x1 and x2.
So just x1, x2?
Okay, x3
That's
as
fine.
well.
Sorry, you might have spoiled the surprise. Yeah, so the easiest starting point would just be to start with all three. Right? See if they're linearly independent because they already span this space, right? So if they're linearly independent, we have a basis, we're good. If not, then we're going to know that at least one of those vectors is a linear combination of the other, but the spans are still going to be the same. I just got to find a linear set. And what you find out is what you said, it's going to actually just be x1, x2 is going to be your linearly independent set. That's why I was surprised. I was like, dang it, you stole my punchline.
Professor, you said we know it spans the thing. Why? How you know it spans already before you even doing it?
So well, I mean, I don't know already. Well, actually, sorry, you're not talking about the question. I thought you were asking, so linear independence, we got to test that. I'm not finishing that word, right? The second thing is if the span of those vectors equals my vector space. But what space am I trying to build? What space am I trying to find a basis for?
R3.
Not R3. We're trying to find the dimension of what?
X1, X2, and X3.
The span of x1, x2, and x3. All linear combinations of these vectors x1, x2, and x3, which means the span of x1, x2, and x3 is the span of x1, x2, and x3. So if we go ahead and start with just those three vectors, we're already given that the spans are the same, right? This is just a straight up easy logical, it's a straight up easy logical statement because those sets are the same. I don't have to worry about finding a spanning set as well. We're already given it. I just got to figure out whether or not these are linearly independent. Okay, so let's work on that. Are the vectors 2, 3, 1, 1, 1, 1, and 3, 5, 1. Are they linearly independent? All right, well, let's see now. I'm going to keep going. I was going to get y'all to work on it, but I want to actually be done relatively close to 150. The shortcut, since we're working in R3, is just throw these vectors into a matrix and then calculate the determinant of that matrix. So 2, 3, 1, 1, 1, 1, 3, 5, 1, and I want to calculate the determinant of that. And I can do it along any row. What row do y'all want to do the determinant calculation on?
Third row.
Third row? All right. So since it's an odd number row, we take the pattern plus, minus, plus, minus, plus, minus. So this will be at 1 times the determinant of 1, 3, 1, 5, minus 1 times the determinant of 2, 3, 3, 5, plus 1 times the determinant of 2, 1, 3, 1. So I'm just multiplying everything by 1, so you just got to find the determinant of those three 2 by 2 matrices, which will be a 5 minus a 3 minus a 10 minus a 9 plus a 2 minus a 3, which is a 2 minus a 1 minus a 1. So the determinant is 0. So what can I conclude? Are these vectors linearly independent or linearly dependent?
You're dependent.
Yeah, they are linearly dependent. So can these three vectors end up forming a basis for the span? Yes or no?
Yeah.
They can?
I think
I think they have to be linearly independent.
Yeah, they have to be linearly independent to form a basis. And they have to be linearly independent. So if you look at this, you can either do this through row reducing and you'll get to see what vectors you need to look at. But that last vector, 3, 5, 1, that's actually just 2 times the first vector plus -1 or subtract the second vector. So the third vector in that list can actually be written as a linear combination of the first two. I can combine the first two vectors in a particular way to recreate the vector 3, 5, 1. That is why they're not linearly independent and are linearly dependent. So we get two things. The span, anything that is in the span of those three vectors, which we refer to as x1, x2, and x3. And if you don't remember, that is absolutely fine. I'll write them in red underneath. Anything that x3 contributed to this span can be covered by the vectors x1 and x2, which means the span of x1, x2, and x3 is just the span, really, of the first two vectors. I only need to use those first two vectors, which we called x1 and x2, to recreate this span. So then the next question is, are those two vectors 2, 3, 1 and 1, 1, 1 linearly independent? Because we see with this observation right here, where I just drew that blue check mark, we've got the second property that we need to form a basis with my set of vectors. It spans the space that I'm caring about. These two spans are the same because I'm caring about finding the dimension of this vector space, which is the span of those three vectors that were given. So if it's linearly independent, I've found a basis, and then once I found the basis, I'll know the dimension. So if I threw this into my equation that I always need to set up for linear independence or dependence, 1, C2, I'll get a system of equations. And what that system of equations will say is that 2C1 plus C2 has got to be equal to 0. It's going to tell me 3C1 plus C2 has got to be equal to 0, and C1 plus C2 has got to be equal to 0. And what is the only value of C1 and C2 that will make all three of those equations true?
0.
Only going to be 0. So are these two vectors linearly independent? Whoops, you played the quick unmute and mute yourself game and I didn't get to hear an answer.
Yes.
Yeah, they're linearly independent. The only way that this linear combination, the linear combination of these two vectors will be equal to my 0 vector is if C1 and C2, my coefficients are 0. So we got to sum it all up. I got to get a new board. So we're just considering the set of 2, 3, 1, set of vectors 2, 3, 1, and 1, 1, 1. First off, we know that they are linearly independent. They're linearly independent. And the span of these two vectors, I'll actually write them out this time. I'll write above it just in red because we've been going back and forth between calling these x1 and x2 and writing them out. But the span of these two vectors is the span of the vector space I'm trying to find the dimension of. The span of 2, 3, 1, 1, 1, 1, 3, 5, 1. So this set of specters spans my vector space that I care about. So it is a basis. Oops. It's a basis for the vector space, which is the span of those vectors. 2, 3, 1, 1, 1, 1, and 3, 5, 1. Thus, the dimension is what? What is the dimension of the span of those three vectors? See, Ellie even giving me the number. Anyone else?
It's 3.
Not 3.
Oh, 2 then.
2, right? Because dimension is how many vectors are my basis. Right? We found a basis for this vector space, and I see that there's 2 vectors in there. So the dimension is going to be 2. And the dimension is going to be 2.
So the span on the basis is the same thing?
Do what? Sorry?
The span on the basis is the same thing.
The span of the basis should be recreating this vector space that you're trying to find the dimension of, yes. And these two spans are equal because, as we said, that vector 3, 5, 1 is just a linear combination of these two. So let's write it out. Did I write that out? No, I need a new board. Let me get rid of this one. So anything that would be in the span of what we're calling x1, x2, and x3, and nowhere over, means it is a linear combination of those three vectors. So 2, 3, 1 plus C2, 1, 1, 1, 3, 5, 1. That's what things look like in the span of x1, x2, and x3. But we said that 3, 5, 1, I can rewrite as a linear combination of the first two. So the first two things stay the same. I'm not caring about those. But then this is plus C3 times the vector, or times, get rid of that, times 2, 3, 1, plus -1 times 1, 1, 1. And just rearranging all of this stuff. Two, 3, 1 plus C2 minus C3, 1, 1, 1. So really anything that you try to recreate or create as a linear combination of those three vectors is really just a linear combination of the two vectors that we found to be the basis, 2, 3, 1, and 1, 1, 1. That's why we can make that statement. I just don't have enough room, so I have to go back to the x1, x2. That's the proof of it. All right. I want to go back to the other board, but I'm going to leave it here just in case y'all writing that down. Any other questions? Oops, that's not where I wanted to go. Any other questions? All right, we're really late today. It's 1:57. I'm going to go ahead and stop the recording. If y'all want to get out of here, you're more than